Hello everyone, welcome to the fourth lecture on displacement sensors and accelerometers, and essentially this is the second lecture in the accelerometer only. Okay. In the previous class where we talked about basic characteristics of accelerometers including sensitivity, cross axis sensitivity and others, we also discussed about different type of accelerometer that is possible. Mostly it was capacitive, piezoelectric, piezoresistive and thermal accelerometers, right. So what we are going to do today is we will talk about different type of accelerometers, and we will see in very brief that how they can be fabricated, and we will also see their advantages and certain limitations associated with particular type of accelerometer, and I mean that is the reason that people look around for other kind of accelerometers. In the discussion we will talk about capacitive accelerometers first. Okay. So a capacitive acceleration sensor essentially contains at least two components. The first is a stationary plate which is connected to a housing, and the other is a plate which is attached to a inertial mass which is basically free to move inside the housing. If you remember, in the previous class we have talked about this inertial mass. We have seen its different name like proof mass, inertial mass, etc. Okay. So this inertial mass is attached to one of the plate of the capacitor and the other plate is connected to a housing. Basically it is a stationary plate. Okay. Now these plates, these two plates, the housing plate, the plate which is connected to housing and the other plate which is connected to inertial mass, actually makes a parallel plate capacitor. Okay. So these plates form a capacitor whose value is a function of the distance d between the plates. Like any other parallel plate capacitor, this two plate, one which is connected to the housing. Okay. So this may be a housing in which there is another plate through which this proof mass is attached, and this proof mass can move or this can accelerate. Okay. So these two plates actually make a parallel plate capacitor, and this is of course a function of the distance d between the two plates, right. Now this capacitor value is modulated by the acceleration of the proof mass. Of course the plate is also moving, but essentially we are talking about this acceleration in terms of the proof mass. Okay. So maximum displacement which is measured by this capacitive accelerometer is maximum around 20 micron, not greater than that, because this capacitive value may be nullified for larger distance. Okay. However, if you see, this is a very small change, 20 micrometer change we are talking about, which is very small. Okay. So this kind of small displacement actually require lot of compensation of drifts and interferences which can easily result into a say false positive. Okay. So there are certain ways by which this can be nullified. One such solution is using this capacitive accelerometer in a differential mode, or we call it differential technique, where an additional capacitor is formed in the same structure of this microfabricated capacitive device. Okay. The value of the second capacitor must be close to that of the first. Of course it cannot be equal, because you cannot make two very identical capacitors. Of course when I am talking about the range of a few tens of micron, I am talking about those kind of capacitors. So not easily you can make them identical, but it should be identical to each other as it can be. Okay. And the second capacitor should be subjected to change with 180-degree phase shift. Okay. Then acceleration can be represented by a difference in value between two capacitors. We will see that these differences are very much essential, particularly when you talk about MEMS based capacitors. So we will see one example of this differential capacitor once. Okay. Because this is the backbone of a accelerometer. Most of this the accelerometers that you see in common applications are mostly capacitive. Okay, so we should understand this differential technique which utilize this capacitive principle. Okay, so this is a cross sectional diagram of a capacitive accelerometer, a practical capacitive accelerometer, where an inertial mass is actually sandwiched between two plates, which the top plate I am calling it as cap or upper cap. Okay, and the bottom is known as base. Okay, so this proof mass or inertial mass is sandwiched between two plates. This is the cross sectional view of this, and this is the top view of this. Okay, the mass is supported by 4 silicon springs. Okay, this you can see in the top view. Okay, the upper plate and the base are separated from it by a distance d1. So D1 is basically D1 is the distance between this proof mass and the upper cap, while this D2 is the distance or the separation between the proof mass and the base. Okay, so if you see, there are 3 different parts: the upper cap, the base, and the proof mass. Okay, and all 3 parts can be micro machined from a wafer or from a silicon wafer. Okay, that's why I'm telling you that this kind of device are CMOS compatible. Okay, or MEMS compatible. Okay, so first parallel plate capacitor that is formed between this mass and this cap, say C. Okay, I'm calling it CMC. Okay, between the mass, the proof mass, and the cap electrode. Okay, so this capacitor between these two is CMC, and this plate area is say S1. Okay, and D1 is the plate spacing between this, and if this mass, for example, due to some acceleration, okay, moves towards upper plate. Okay, now say initially it was at this place, and if it moves by a distance delta, okay, to this new position, okay, this has moved to this new position, means that the D1 value, actually the separation between this mass and the upper cap will decrease. Okay, so earlier it was this one. Okay, now it has reduced to this one. So basically it is D1 minus delta, right? So this, when this mass moves in the upward direction because of acceleration, the distance between this mass and the plate decreases by a value delta, and this value is D1 minus delta. All right. Then there is a second capacitor which is of course associated with the mass and the base. I am calling it CMB, and this has a plate area, for example S2. It does not have to be equal to S1. Okay, so S1 and S2 not essentially should be equal, they can be non-equal also. Okay, now this CMB, this was CMC, CMB is between the mass and the base. All right. So when we are considering the case when this mass has moved towards the upper plate by a distance delta, and since this mass has been lifted towards this direction, distance between this mass and the upper plate has decreased, and the new separation is D1 minus delta. Similarly, since the distance remains same for this capacitor also, CMB also, so the gap between this base plane and base plate and the mass will increase. Okay, and the new distance is D2 plus delta, right? So this will of course will directly affect the two capacitances between mass and the upper plate and mass and the base plate, right? And the value delta, since this is kept on silicon springs, okay, this mass is supported by silicon springs, okay, the value delta is equal to the mechanical force acting on the mass divided by spring constant of the silicon springs, or delta can be given by force by the spring constant of the silicon. All right. So you can directly find this delta, and by using a proper integrated circuit with this capacitor in picture, okay, you can find the acceleration in terms of this value, and by comparing that with the force that is applied, you can find the acceleration. Okay, we have seen that in our first lecture, right? So this is just one way to design this capacitive accelerometers. There can be a number of ways. This number of ways will depend on what is changing. There can be change in area, there can be change in the parallel plate structure, there can be change in the buried oxide layer, change in the dielectric material. Okay, this we have just now seen an example where the distance between the two plates were changing. Okay, so you can essentially design n number of capacitive accelerometers by varying the parameters like this, but you have to have a proof mass or inertial mass which is being affected by these changes, right? So by this mean you can actually design different capacitive accelerometer. There are several advantages associated with this capacitive accelerometer, like their high sensitivity, their low power consumption, they are compact because these are MEMS devices, they are compact and of course lightweight. Okay, since batch fabrication is possible, they are mostly inexpensive. Okay, and they are of course suitable for integration with digital electronics. Okay, however, there are certain limitations like any other capacitive devices, like they are limited by their frequency response. Okay, they are affected by the temperature changes, and they will of course require external signal conditioning, okay, particularly for taking the data and taking into consideration all these 2 or 3 capacitances which is forming. Okay, so they require signal conditioning. Okay, and the signal conditioning circuits are not that easy, particularly this kind of differential capacitor arrangement based accelerometers. Okay, so you can consider this as one of the limitations. Okay, however, their applications are tremendous, like in automotive they are used for airbag deployment. Okay, in smartphones they are very popular. For inertial navigations they are used in satellite also. Okay, for vibration analysis, motion tracking and fall detection, for example, they are very popular. Okay, so we have seen certain limitations of capacitive accelerometers, and that's why there were a requirement of other kind of accelerometer. And let us see one of the other alternate accelerometer which is based on piezoresistivity. So let's talk about piezoresistive accelerometers in very brief. Okay, so the detection technique of this type of accelerometer relies on the change in the resistivity of the piezoresistive material. Okay, like any other application of piezoresistive materials. Okay, and this changes is caused by mechanical strain due to some forces, which is of course the reason for acceleration. Okay, so as a sensing element, a piezoresistive accelerometer incorporates a strain gauge which can be glued also, like any other strain gauge based device. Okay, so it incorporates a strain gauge that measures strain in the mass supporting springs. Okay, the strain can be directly related to the magnitude and rate of the mass displacement, and once you have this mass displacement calculated, you can of course calculate the acceleration. Okay, so a typical piezoresistive accelerometer which is fabricated looks like something like this. Okay, if you see, essentially it contains 3 layers of silicon. Okay, the inner layer is the core layer which consists of inertial mass. Okay, the inner layer contains this inertial mass. Okay, this one. Okay, and the elastic hinges. Okay, the mass is suspended inside the edged rim on the hinges. Okay, like this. These are hinges. Okay, and they have been etched. Okay, from silicon only. Okay, now piezoresistive gauges are placed on either side of this inertial mass. Okay, now these strain gauges, the piezoresistive strain gauges detect motion about the hinges of this proof mass. Okay, the outer 2 layers are basically a base and a lid. So we have talked about 3 different layers. This is the internal layer which contains the inertial mass, and then 2 different layers. One is the base and another is the lid. Okay. Now this has 2 functions. One is they will protect the moving part. This moving part is this inertial mass. Okay. So this lid and the base will protect the moving part from external contamination. Okay. When acceleration is applied along the sensitive axis, the inertial mass moves around the hinges. Okay. And there are certain recesses which are actually edged out from the base and the lid. Okay. So when these recesses are formed by deep etching this base and lid, this inertial mass actually can move or can rotate inside this recess. Okay. So the gauge is, please note that, is placed on either side of this proof mass. Okay. So the gauge on both sides of the hinge allow detection of the movement of the mass. Okay. So actually when acceleration is applied along sensitive axis, the inertial mass actually the movement is rotatory. So actually it rotates around the hinge. Okay. And this rotation along the hinge will create 2 different stresses. So it will create a compressive stress on one of the gauges. Okay. At the same time it will apply a tensile stress on the other one. Okay. Now these gauges are very short. Okay. So even a small displacement produces a large change in the resistance. Okay. So now to trim the zero balance on the piezoresistive bridge, there are 5 trimming resistors positioned on the same crystal. However, it is not shown in this photograph. Okay. So this is a typical fabrication technique of how piezoresistors can be used by placing them around a hinge which is connected to a inertial mass, and this kind of setup can be used for measuring the acceleration. The advantage of this kind of system is they have very decent sensitivity and they can operate over a wide temperature range. Okay. They are suitable for low to medium frequency applications, and their power consumptions are also not very high. Okay. So there are certain limitations also associated with this piezoresistive accelerometer, like they are sensitive to temperature induced drift. Of course, you can compensate it by certain fabrication techniques, but then it is definitely sensitive to temperature induced drifted, particularly if the resistance is involved. Okay. It requires regular calibration, and the power consumption is although moderate, but it is at a higher side as compared to a capacitive accelerometers. Okay. Therefore, we have another kind of accelerometer in picture, which is the piezoelectric accelerometer. Please do not get confused between piezoelectric and piezoresistive. We have talked about the differences between piezoresistive and piezoelectric in more detail in our initial modules. Okay. So the piezoelectric effect has a natural application in sensing vibration and acceleration. The effect is a direct conversion of mechanical energy into electrical energy in a crystalline material which is composed of electrical dipoles. Okay. This we have already seen in detail when we talk about piezoelectric sensors. Okay. These sensors typically operate from a frequency range of as low as 2 Hz up to 5 kilohertz. Okay. And the advantage of using these accelerometers are they possess a good off-axis noise rejections and high linearity. Okay. Similar to the piezoresistive device, they can operate over a wide operating temperature range, but they are not very much affected by the change in the temperature. So piezoresistive devices were more susceptible to the ambient temperature changes as compared to piezoelectric accelerometers. Okay. We know that quartz possess the piezoelectric property. Of course, silicon doesn't have it. Okay. That's why we have to look for other kind of materials. So natural quartz have this kind of piezoelectric property. So quartz crystals are occasionally used as sensing element. However, most of the time these devices rely upon ceramic piezoelectric materials. For example, barium titanate, lead zirconite titanate PZT, which is very popular, and this lead metanoite. Okay, so they are very popular. Out of this, PZT is of course very popular for piezoelectric accelerometers. Okay, so a crystal is, if you see the construction of this piezoelectric accelerometer, a crystal is sandwiched between the case and a seismic mass. Seismic mass of course is the same name for the inertial mass or the proof mass. Okay, so this is the crystal I am talking about, and this is sandwiched between a case, the outer lid which is used for protection basically, and the proof mass. Okay, now this exerts the case and the seismic mass that exerts on it the force proportional to the acceleration. So when you apply the pressure, this piezoelectric material is directly get deformed. Okay, so in a miniaturized sensor, a silicon structure can also be used. However, silicon doesn't have piezoelectric property. So basically a thin film of lead titanate can be deposited on a micro machined silicon cantilever, which can provide basically this lead titanate can basically provide a piezoelectric property. Okay, so you have this this piezoelectric accelerometer on which this material is deposited, and when you talk about this thin film kind of devices, they are very miniaturized kind of device. Okay, there are a number of advantages associated with this piezoelectric accelerometer. They are highly reliable, they are compact and lightweight, they have excellent high frequency and shock measurement behavior. Okay, they have long operational life as well as longer shelf life. Okay, however, there are certain limitations, like they are ineffective for static or low frequency measurements, while they are sensitive to base strain and thermal effects. Okay, they also require some, particularly certain kind of piezoelectric accelerometer definitely require charge amplifiers, because the output is in the form of charges, and charge amplifiers are basically difficult to design. Okay, so we have another kind of accelerometer which is based on thermal principle, and we call it thermal accelerometers. Okay, so thermal accelerometers are although the name suggests it's a thermal devices, but basically it is also fabricated on the MEMS platform. So thermal accelerometers are also essentially a MEMS based sensor. Okay, they measure acceleration by monitoring the change in heat flow within a sealed cavity. We will see that how this is measured. Okay, so mostly these thermal accelerometers are of two type. One is heated plate accelerometer, we call it HPA, and another kind of device is HGA, which is known as heated gas accelerometer. In today's lecture, we will see what is a heated plate accelerometer. We will take up the HGA or the heated gas accelerometer in our next class. Okay, so let us see what is HPA or heated plate accelerometer. Okay, so but before I go into the topic of HPA, let us quickly recap the heat flow mechanism. Okay, so the transfer of heat in a gas or in a fluid by the molecules of the medium occur by one of the method, either by conduction or by convection. Okay, however, if we choose proper conditions, when I say proper conditions, mean proper orientation of the structure of the plates, the gas pressure inside those enclosure or the enclosure gaps. Okay, if we consider it properly, the convection can be neglected, and it will only appear that conduction is happening. Okay, however, these conditions is very difficult to create, and it can be however created in a small MEMS based cavities. Okay, now a thermal accelerometer, as any other accelerometer, contains a seismic mass. We have already seen. This mass is suspended by a thin cantilever. Okay, this cantilever is positioned across in a close proximity with a heat sink. Okay, or sometime it is kept in between two heat sinks. Okay, something like this. So you have this two heat sinks and a heated plate placed over here. Okay, and it is filled, the chamber is filled with the thermally conducting gases. Okay, So the mass and the cantilever structure are fabricated using any micro machine technology. Okay. So the space between these components are filled with a thermally conductive gas, as I have mentioned. Okay. Now the mass is heated by a surface deposited or embedded heater. Okay. So on the cantilever you have already placed some heater element, okay, which can be easily patterned in the MEMS technology. Okay. So this heater can take the mass to a temperature of say T1. Okay. Under the no acceleration condition, means when there is no acceleration at all, a thermal equilibrium is established between the mass and the heat sinks. Okay. The amount of heat Q1 and Q2 conducted by the heat sinks through the gas from the mass, because the mass is being heated, is a function of distance m1 and m2 from the mass. This distance is between mass and the heat sinks, the two heat sinks I have talked about. Okay. Now the temperature at any point in the cantilever beam supporting the seismic mass depends on its distance x from the support and the gap at the heat sinks. It will depend only on these two parameters, and it can be easily found by the second order differential equation d square t by dx square minus lambda square t is equal to 0. So this is a second order differential equation, and if this lambda parameter is equal to, this has been found by finding the solution of this particular equation. Okay. Lambda is equal to under root kg m1 plus m2 by ksi d into m1 into m2, where d is the thickness of the cantilever beam, this ksi is the thermal conductivity of silicon, kg is the thermal conductivity of gas, and m1 m2 we have already seen is the distance between the plate and the heat sinks, right. So heat sinks at a temperature T naught. Okay. Now the boundary conditions are T at 0 is equal to 0, dt by dx is equal to, you can easily find it by differentiating this, and this is equal to P by WD KSI, which is the thermal conductivity of silicon, into lambda square T is equal. And now if I equate it to 0, I can easily find this Tx as P sin lambda x by WD KSI lambda into cos hyperbolic lambda L, where W and L are the width and length of the beam and P is the thermal power. Okay. This equation is very crucial because this will govern the accelerometers or the behavior of the accelerometer. Okay. So to measure this temperature, this has to be measured because this is a function of x, right. So to measure that temperature, a temperature sensor can be fabricated by depositing temperature sensing material directly on the beam, because you do not have any external measure to detect this temperature. Okay. This can be done by integrating silicon diodes into the beam, or it can also be done by forming serially connected thermocouples or a thermopile on the beam surface directly. Okay. So the measured beam temperature in form of an electrical signal is basically the measure of acceleration. Okay. And that is how a heated plate accelerometer works. Okay. The sensitivity of these thermal accelerometer is somewhat smaller than that of a capacitive or piezoelectric type. However, they have their own applications. Okay. The advantage of this kind of device is it is much susceptible to interferences, as ambient temperature interferences or electromagnetic interferences, or be it electrostatic noises, because once these gases are trapped inside it, it only depends on the internal conditions, not on the external conditions. Okay. Another advantage of this kind of device is they are CMOS compatible. You have seen that you have fabricated everything by micro machining silicon. Okay. They can detect low G accelerations, okay, and can operate in a high vibration ambient and very harsh ambient. Okay. Till now we have seen that if you require a very harsh ambient kind of conditions, mostly the optical devices are capable, but these thermal devices can equally be be stronger or be compatible with with this kind of conditions. Okay, they have a very robust and compact design, particularly you are making it on MEMS platform, and they have high shock tolerances. Okay, the operational life of these devices are also very high, particularly if you make this cavity very if you trap these gases in very tight conditions, if it is not a leaky kind of structure, if you trap these thermally conductive gases, okay, their operational life is very high. Okay, so so another type of thermal accelerometer is a heated gas accelerometer. Okay, and the behavior or the operation of heated gas accelerometer is totally different as compared to the heated plate accelerometer or the HPA. Okay, so what we will do is we will understand this heated gas accelerometer or HGA device in our next lecture. Okay, we will continue our discussion on accelerometer in our next lecture also. Thank you.